The Erf function returns the integral of the Gauss error function over an interval of values. In this video, we will generate the dataset of the the error function, the Erf function. So RA formula, Erf, the Gauss error function of these values of x. Here you will find this trend line from -2 to +2 values of x, and also the trend line equation to the 8th degree. So we have B0, B1, B2, B3, B4 until B8. The error function is also defined as 2 over square root of pi times the Gaussian integral. So the Gaussian integral is the series sum, or the summation of a times x to the 2n plus 1, where a, the coefficient, equals -1 to the power n over the product of n factorial and 2n plus 1. Our values of n here for now will generate from 0 to the maximum of our data set. The result will be an approximation of the Erf function. You begin with the coefficient, so RA formula. Let's start with the denominator, that is factorial of n. So that's the first part of the denominator. We'll complete the denominator. So we multiply 2n plus 1 to the factorial. 2 times n plus 1. Now that we have the denominator, we continue with the numerator. There are two parts, -1 to the power n. So this is -1 to the power n. And we factor in 2 over square root of pi. So before we do that, let's show the Gaussian integral, which is equal to SERIESSUM, RA formula, SERIESSUM of the x values raised to the power. For the first term will be 2 to the n plus 1. So at n equals 0, the power of x is 1. At n equals 1, the power will be 3. At n at 2, the power will be 2 times 2, 5. So 1, 3, 5, there's the interval of 2. So, and the coefficient will be this range. You'll see this is the Erf function in blue, while the Gaussian integral in red. To make them equal, we will factor in 2 over square root of pi to the coefficient. So we multiply 2 over square root of pi. 2 divided by square root of pi. Looks like this is wrong. We missed something. That's better. Now they're on the same line. Let's check the coefficients. B0 is 0. B1, 1.12. B2, or 0. B3, negative 0.353, negative 0.348. There's a bit of an error. B4 is 0. B5, 0.073, 0.078, 0.073. B6, 0. And B7, negative 7.38. Now it's far up, negative 5.83. Negative 7.38 times 10 to the minus 3. This is negative 5.83 times 10 to the minus 7. So there's an error as the degrees, the exponent goes higher. We'll calculate these values using LINEST. To do that, we will generate the 1 comma x matrix. So this will be, the power will be from 0 to 1 to 8. So Rf transpose these values. And we generate the 1 comma x matrix. So we're starting with the 1 column. So Rf formula of the x values to the power 0. That's 1 column because any number raised to the power 0 is 1. And we lock the reference to copy the formula. So we go to the x column. That's the x column, matches to our x values here. Next, we generate the x squared column, x cubed column, and so on. Now we can calculate the LINEST. Let's begin with the Erf function itself. So LINEST data y and data x. And let's check our B0 is 0. B1 is 1.12. B2 is 0. B3 is negative 0.352, negative 3.353. B4 is 0. B5 is 0.078. B6 is 0. B7 is negative 7 point, so this should be scientific. 7.38 times 10 to the minus 7, and B8 is 0. We take the LINEST of the Taylor Maclaurin series of ERF. So our LINEST of the Taylor Maclaurin series of the ERF, the expansion, and data x. So B0 is 0. B1, they're the same. So 1.12, B2, 0. And B3, negative 0.348. That's correct. B4 is 0. B5, there's a bit of difference, 0.0732. And B6 is 0. And B7, we change it to the scientific. That's 5.83 times 10 to the minus 3. This completes the Taylor Maclaurin series sum of the Erf function and the LINEST polynomial regression to the 8th degree of the Erf function.